present in the session right now. Uh, Dr. M. Chandrasekhar Reddy, sir, your camera is on. Please turn it off. Okay, thank you, sir. Mr. Vishal, first of all, let me introduce you to the participants. We are having registration of 200 participants across the India. They all are academicians from different institutes, and they are attending the sessions regularly. Now, let me introduce yourself to all the participants. Mr. Vishal Katba is a senior manager of engineering branch of Intel Technologies India, Bangalore. Vishal Katba is post graduated in the VLSI design. Sir is having 15 years of experience in the field of physical design in the VLSI domain only. He has worked with various reputed industries like Intel, Qualcomm, Freescale, ST Microelectronics, and so on. Up to now, sir has tapped out more than 35 chips successfully for mobile phones, then clients, then AI, that is artificial intelligence, then network and automotive SoCs. And currently, Mr. Vishal is working as a leader in the neural processor SoC PD division in the Intel Bangalore. Uh, Welcome, Mr. Vishal. On behalf of Electronics and Communication Department, Government Engineering College, Rajkot, I, Dr. Dhaval Bhojani, heartily welcome you and thanking you for sparing valuable time for us and our participants. So now the session is over to you, sir. Thank you very much again.
Thank you, Dhaval sir, and thanks for the introduction. And thank you all. So first of all, I'd like to thanks for this opportunity, and I really hoping that all of the participants and their family are safe and secure in this pandemic. So thanks for this opportunity. And so today I'm going to kind of present. Let me share my screen, I think, and then we'll start. So today our discussion topic is. Are you able to see all?
Yes, it is. Yes, it is visible.
Yeah, so today's our topic is floor planning and the placement for the physical design flow, right? So I have kind of seen that you already had a very nice sessions on quite good, interesting topics for the VLSI design flow prior to me, and hope all of you have a good learning with all of this one. And so there are some prerequisite for this presentation that I hope all of you have gained during the previous session. So those are kind of a basic RTL understanding, your basic synthesis, what it is, and basic of timings, right? And as an electronics engineer, right? So all of you might have the basic, probably as you are teaching, right? So you will have a detailed understanding of your CMOS design, digital design, and the basic of semiconductors. So these are the basic prerequisite for this course, and I'll be kind of taking you through the floor planning and the placement flows of the physical design, right? So before we start, I think let's make this session more interactively and more interactive. And all of you, I think I request you to ask question if you have any, so that we all feel connected and don't feel sleepy. Okay. So let's start it. So before we kind of start, I just wanted to give some recap of what is our ASIC design flow, right? So I think all of you have already a session on the what is the flow, what is the flow, how it works, and what are the steps it has, right? So I just want to exactly these steps. So as requirement for any application. So that comes with an idea. So generally, all the marketing people who kind of deal with an industry, right? So they go and come up with ideas saying that this is the current market trend. This is what we can go ahead with the SoC, which can fit in so applications, and that can give us a probably a certain revenue, right? So that idea is fed to the architecture team. Architecture team collects all of these ideas and come up with a kind of a blueprint that is overall architecture plan, what you can say. So that they kind of first understand the functionality of that idea, and they come up with the need, right? So need, it's in terms of, for example, if you want to develop any application, so what will be the what all are IP required? So IP is probably it's intellectual property, but in layman term, if you can say, this is the set of functionality you require, right? So like, for example, you require PCI for your IO, you require USB for your IO, you require a neural processor or the application processor or the DSP processor for your processing, right? So all of these requirements together, and they kind of tune all of these IPs with based on the frequencies or the throughput or the power what they require to deliver, right? So they kind of come up with the need, okay, this IP has to work with these frequencies so to meet this particular performance. So in a way, they come up with a kind of a blueprint of the architecture which can fulfill and meet the desired idea, and that blueprint or the architecture plan shared with the RTL team. So from here, the actual the engineering work starts, or we can say the front end work start, what we can say, right? So that our particular architecture has been coded in our RTL. So that can be Verilog system, Verilog, or C-based RTL, right? Or that RTL get validated and kind of run through the various testing, and then that goes to the silicon design team. Silicon design is what we call also a physical design team, right? So physical design team kind of take it that RTL and make it a foundry ready, so that that can implement that they'll implement transistor based design which can be fabricated and that can fulfill the functionality of what initial our idea was, right? So that's the primarily the ASIC design flow is, and I think all of you are aware with it. So now let's kind of go and understand how the silicon design or the physical design flow works, right? Okay, so yeah, so this is our traditional physical design flow where you get RTL, right? So or the front end collaterals from the RTL design team, right? So that is your all of what we got is a Verilog system, Verilog or VHDL code or low power format. That's a low power specification that what all are the power conditions for each of the module, standstill and the memory libraries, and sort of constraints saying that this block will work on these frequencies and these are the real path, these are the false path. And then it goes to the synthesis where you kind of map this RTL to standstill libraries, and then you do the DFT insertion, then the optimization, then it's a floor plan, so which will go through. I'll just kind of skip this thing here. Then the place and route, and then all the sign off, right? Any question? Okay, so sign off is specifically what all of us, we are checking is whether our performance is meeting, whether all the foundry rules are meeting, whether our implemented design is matching with the RTL or anything is changed functionality wise, right? All the low power needs are meeting, all the our dynamic and static power requirements are meeting, right? So all of this sign-offs we do at the end of the physical design, and then we kind of write the GDS to a foundry. So this is our traditional design flow where what we have is we do a synthesis and the place and route and the sign-off, right? So that has worked very well till all the reasonable size of technology. But as we started shrinking the technology where all the performance needs are kind of traditionally changing, and all the shrinking technology has a various rules that has to be adhered, right? So this traditional flow requires some changes, and industry-wise, I think there is a totally shift on transition towards moving to the bit optimized flow, which can deliver the better performance overall compared to the traditional flow. So let's see this. So right, so this is our advanced flow, what I can say, or which is overall, I think industry-wise, as of now, people are using for all the lower 3, 5, 7, 10 nanometer kind of technologies. So what is the difference here is, now the synthesis and the floor plan stage, right? So that's kind of now not a different one. Previously, we used to have first set of synthesis, but this is something like what we get as an RTL. Then we elaborate the RTL, kind of reading the RTL, saying that everything, the syntactical and everything is proper. Then we map it to a standard cell library. This was the part of synthesis, right? And then we do a floor plan. So previously, if you see our previous stage, right? So the synthesis, then the floor plan was coming. Now synthesis is divided into two. Your first mapping only is here. Then you do a complete floor plan. Then you do a synthesis optimization. Then the remaining place and route stage are stay as it is. Now, why we need to do this is because so when we are previously doing a synthesis, we didn't have any knowledge of your actual physical context, right? So whatever we are doing is only a logical. So you don't know whether where is my boundary ports will sit, from how much travel, how much distance I need to travel from the port to it, by the time it reaches to the flow, right? And from the flow, how much time I requires to go to the output, where will be my memories will be sitting, how long distance I have to travel between two flops, right? All of this detail will not be there if you do a default synthesis. But once you have a floor plan and then you do a physical aware synthesis, then you will have all these details, and synthesis can do a better job compared to a default logical synthesis. Okay, and this is completely nowadays complete flow is a physical aware. So from the very beginning of your synthesis till your final route, so everything is a physical aware. So you don't miss the context of and physicality of your design. So the primary topic what we are going to discuss today is the floor plan and the placement. These are the two topics which we are going to cover, and let's go one by one, right, and understand it. Okay, so first of all, floor planning, right? So floor planning, what is floor planning? So floor planning is a way of physically architecting your design such a way that you can achieve a best power, performance, area, and turnaround is a kind of a time to implement the design, right? Turnaround time for SOC for a given technology. So it is a kind of a way of physically architecting your design. So before you kind of implement your transistors inside your design, before you kind of connect it in between, and so this is the simplest way of defining your physical context where your silicon or where your SoC is going to build, right? So and there are various prerequisite for implementing the design, right? So before that, you need to meet all the Foundry rules, you need to meet all the design criterias, right? You need to meet various semiconductor rules, the whatever we have in semiconductor field, right? So those all requirements we need to meet, and for meeting that, we need to first come up with the proper area where you wanted to place and route your design, right? So this is the kind of a step to define physically how your SoC will or the partition will look like. So there are two portion of the floor planning. One is partition level floor planning, one is SoC level floor planning. So SoC is something all of us know. This is the one full functionality which we kind of use it in our all the electronic circuitry. But inside each of the SoC, it's divided into a multiple partitions. So the floor planning happens at the two level. One is at the SoC level, and then individually all the module level inside that SoC. Okay, so there are various tasks involved in the floor planning, and I'll just not read it out, but we'll go through each of these and try to understand what all of these are. But I think if you see the name, right? So floor planning is something it's very much matching with your when you do a floor planning of your house, right? So, and it is as fun as designing your own house floor plan, and you will kind of enjoy this, and you will be able to correlate it very well, saying that, okay, why I need to do all of these things, right? So I'm just putting this analogy to kind of keep you connected and kind of create some reference which you can correlate with, right? So, okay, let's go and understand what is a floor planning. So first of all, before we start a floor planning, what we need to understand, right? So, so if you see the couple of first steps, right? So this understanding of your design flow is very much important. Design and data flow. So let's understand what it is. So whenever you are whenever you start designing any of the SoC, right? So first of all, what you need to understand is what all modules I have in my SoC, what all are the various functionalities I have it, right? And how my data is moving from one module to another module. Likewise, let's take an example of this one, right? So we have a one input unit where, say, for example, you are getting a data. Then there is a one transit unit, you can say hierarchy one, which kind of receives the data from input unit and it transfer it to hierarchy three. And hierarchy three is, say, for example, it's a processing engine which decide what kind of operation I wanted to do. And based on that operation, it sends the data to hierarchy 5 or hierarchy 2 or hierarchy 4. And based on these operations, right, it can, the other hierarchies can send a data to another hierarchy, or it can send a data directly to the output unit. So this is just an example, I'm putting it here, right? And the same way it goes to the output unit, and output unit can send a data back to the board or wherever you want to connect this SoC, right? So this kind of basic understanding of design flow is very, very much important, because based on this understanding only, you will able to kind of plan your SoC, right? So if you have a knowledge of, say, this is my data flow, then what you will do is you'll place your input unit next to your IO, then you will put hierarchy 1 next to that one, and then hierarchy 3 in the center, so that all these other hierarchies can talk to it in the very lesser distance. So if you have a basic understanding of the design and data flow, you will able to plan it very well, and you can make sure that you don't waste any area, very first thing, and you have a minimum distance from one hierarchy or one module to another module to travel, and that can meet your performance requirement as well as the throughput requirement, right? So these are the very much basic thing which we need to acquire. And this here, you need to understand whatever is the architecture of your SoC and what is the way it is coded in the RTL, right? So these are the basic things what we need to understand before we start floor planning. Okay, yeah, and moving on. So there are various types of floor plan. So and based on the need and based on the availability of your area, right? So you can plan with you can choose the right way of the floor plan, what you wanted to opt for. So I have given a couple of examples here. One is what we call is a non-abutted floor plan. Non-abutted floor plan means you have your boundary defined, and you have each color coded is your, say, module, right? So one is you can put all the module apart from each other, and there will be a channel kind of going through each of these module. And there is a provision. So here you can put this module, if you can put its boundary ports here or here, anywhere, and can travel through this channel, and it can reach to any of the partitions, right? So this is the non-abutted floor plan. Another way of abutted floor plan is partially abutted floor plan, where you can kind of leave some channel to move the signals throughout it. But wherever it's possible, you're trying to abut it, right? So that you can get rid of all these channels, right? And third one is fully abutted floor plan, where you kind of abut everything and you don't have any channel left. Now the question will be how the communication happen, right? So for example, this partition wants to talk to this green partition, right? So how it will go and talk to? So in this case, it can go through the channel and kind of reach it here. So in this one, there is a concept of feed through comes. Feed through means, so this signals, whatever it has to talk to this partition, it will create a feed through this partition, and it reach here. And it will try. So while this partition will get implemented, it will have a knowledge saying that I have this many signals from partition blue has to reach to partition green, and it will route it and buffer it throughout this partition, and it will make sure that these signals are routed throughout properly. So this is how the abutted floor plan works. The major benefit with abutted floor plan is you don't have any wastage of area, and you will have a well optimized area floor plan. Right? So that's the major benefit of abutted floor plan. Okay, going on. So please let me know if you have any question. I'll just kind of cover it at that slide if possible. Okay, moving on. The next and the foremost step, I think as we start the floor planning, the very first step, what we need is kind of defining your design boundary. Okay. So first of all, why we need to define the design boundary? So it is something, again, I'm putting analogy of your house floor plan. You need to define your area where you wanted to build a house, right? So this is similar way you need to define your SOC area where you want to build your SOC. And so if you kind of come up, right, so each of your whenever you're going to fit your SOC, right, that will be on the board. So you will have any board where you are designing that board, it will have other components, it will have other SOCs, it will have other components, other routes, and everything will be there, and there will be limited area to place inside for your SOC. And wherever this board is going, for example, you are going to fit this board in your PCI slot of your computer, right? So it will have a limited height to fit it, right? So based on that, board will have a limited area, and each of this board will have limited space for your SOC. In similar way, if you come up with the bottoms, right, so you will have each of the hierarchy, whatever you have inside SOC, that will have a dedicated area required to implement it. And if you combine all of this hierarchy, right, so it will have some area which minimum required. So that minimum area is also need to be fulfilled, and the maximum area, whatever available on the board, that has to be fulfilled, right? So based on that, you will come up with some area which can meet the SOC need, right? So that's what you define your design boundary. And how to choose the correct size? So you need to make sure as I mentioned, you need to make sure your all the design, whatever you have, that can be easily implemented in given area. You sum up that complete area, and then come up with this is my core area, right? So so there are two way of identifying the design. One is based on your design size. So if you consider this as in your SOC, right? So you will have an area of your core. The center area is what we call a core. So core area is based on your number of partitions or number of design you have and total area of it. And other is IO, right? For example, your boundary has an IO, right? So all these IO pads, what we put on the boundary, if your pads are so many that many times it itself is deciding your area, because if your pads are so many, you have a limited space to surround by any square area, right? So if your pad are more, you need to increase the size of this core so that your pads can fit. So this is what we call a pad limited design. And another one which is increased because of the core area, that is what we call as a core limited design, right? So these are the mainly two limitations for choosing the SOC area. Okay. Now, so once we have define your design boundary, right? So once you know that, okay, this is my design boundary, and I have created this particular area. So then you go and kind of understand what is your voltage requirement, okay? So voltage requirements come from the UPF. UPF is a power format, IEEE power format, which is used for the VLSI design. And the UPF is having various definitions of your power domains, your power state tables. So I'll try to just touch based on it and kind of explain what it is. So first of all, what is power domain and why we require a power domain? So say, for example, again, if we go back to the our house planning analogy, right? So if you have your house have multiple rooms, and if you kind of put a one switch where you can kind of turn on and turn off your lights, right? So that's not optimal. Generally, what we do is we go and put switch inside each of your room to make sure that each of the room can turn on and turn off individually, right? And it's optimal. So that's the same analogy applies here. So you have a multiple module, and at the given point of time, it's not always necessary that you have all the modules acting or working together. So there is if one particular module is not working in given point of time, and for saving power, what always benefit is to shut off that module and disconnect its power so that you can save the total power in your design, right? So what we call is a power gating. So and that power gating is achieved through power switch, which we'll understand later. So and based on that understanding, we kind of divide the total area into various voltage areas. Okay, voltage area means each of the area which requires a different voltage at different times. So different time is also important, because same voltage is available in both the area, but one particular area doesn't require voltage at given point of time. So both of them require a separate power supplies, right? So separate connections to a power, right? So based on that understanding, we divide the total area into different voltage domains, okay, or power domains, what we can say, right? So for example, let's take an example that this is one power domain, this is another power domain, this is third power domain. So say this is our gated power domain. So gated means here you are doing a power gating, and at some point of time in the operations, you understand that this particular power domain is not really required to be on. So you can kind of gate its supply or put a switch between your supply and the transistor, and you disconnect its transistor from the power. This is always on, which requires to have continuous operation. So you cannot turn it off. And say, for example, this is some different voltage altogether. So this is, say, for example, working on 1.0 volt for both of these. This is can be gated, this can be always on, and this can be, say, working on 1.2 volt. So it has to have a separate rail for this transistor, because you cannot share the rails, as this is getting 1 volt and this is getting 1.2 volt. And there are certain low power requirements. Say, for example, if you're moving from the low voltage to the higher voltage, you need to level shift all of these signals. So you are putting level shifter here. So whenever you are moving from a gated domain to always on domain, you require a isolation here. Isolation is, so for example, when this domain is shutting off, right? So your all of the signals, whatever you have in the boundary, that can go to in the unknown state, and that can drive to a metastability of any of the transistor which is getting driven from this partition to here. So what you do is you put some isolation cell that kind of tie each of the signals to either 0 or 1, and it will have a known state of signal for each of the transistor, whatever it's receiving it. Right. So these are some low power requirements what we have, and based on this, we create a voltage area. Okay. So I hope this is clear to all of you. Moving on, so there are certain rules each of the foundry has, okay, so which we need to adhere, and we need to make sure that we obey all of these rules. So for example, each of the foundry, like you take an example of TSMC, Global Foundry, Intel, right? So it has whatever technology you build, each of this technology is a proprietary technology, and each of this has a certain set of rules which you need to follow for physical design, to make sure your layout, whatever you are drawing, is can be fabricated, right? So, and this all the rules comes up with some as a technology file to us, okay? And these rules includes your, say, number of metal layers what you choose. So for example, if you are using a 10 metal layer process or 15 metal layer process or 7 metal layer process, right? So based on that, these many number of metal layers available for given technology, and this you can route up to that layers only using that technology, right? So you need to understand that. And another is a poly pitch, right? So this is mainly on technologies at 3 nanometer, 5 nanometer. What is your pitch? You can use it for between two different polys, right? So this is the poly pitch. Then there are certain metal rules, say what can be the minimum width of your metal, particular metal layer. So M0 has a different, M1 has a different, likewise M10 has a different, right? So each of this metal layer has a what pitch, what is the minimum spacing required between two continuous metal you are drawing inside your design, right? So that also has to be, all of these rules has to be followed. Next is a DPT. So DPT is a kind of a double patterning, and similarly you will have a triple patterning as well. So if you shrink to a lower technologies, and so it's become very difficult to fabricate the two continuous metal, right? So if you are drawing two metals continuous, there is a limitation. You cannot draw two continuous metal because of your foundry limitations and your light limitations inside foundry. So that what they do is they create two different mask for subsequent metals. So for example, if you are having a if you are having a two metal, 1 second, let me try. Say if you are having a this. So let's say, for example, this is your one metal, right? And say nearby you are trying to draw another metal here. So as the technologies are shrinking up such a way that it's not able to kind of fabricate very nicely all these two subsequent metals. So what is been done is, so there is a different mask created for this particular one, and there will be a different mask for this two, right? So there will be a kind of a hollow in between when you fabricate. So then each of this will fabricated one by one. So there will, the first, say this guys will fabricated where there will be nothing here, and then you will have a mask covering these two as a fully covered, and then you fabricate this particular metal. So you have a two patterns to match eventually here, right? So this is what you call as a double patterning. Similar way, if you 3 nanometer and likewise, you have a triple patterning as well. So you cannot fabricate in a single mask. So you need to create a 3 different masks for each of the layers. So this generally applies on the lower layers of say M0, M1, M2 kind of layers, where you have a very thin metal, right? So there you require this kind of patterning or the multiple mask creation. And likewise there are multiple VR rules as well. So like a metal rules, you will have VR rules, VR to VR spacing, and the VR minimum cut, and all of these rules are there which you need to adhere. So all these rules comes as a technology files, and which all the current industry tools understand very well. Okay, and this automatically they can understand, they can throw you error if something like this you say this is violated, right? So if you adhere this one, that should not be an issue. Okay, hope this is clear. And moving on, so once you have basic this understanding, right? So based on that, we create tracks. Okay, now rows and tracks, which what we need to create. So again, let's take an example of whatever power domains what we have created. And so there are two requirements here. One thing is to create a standard cell rows, and another is to create the metal tracks. So each of this is very much important to understand. So if you see any of the standard cell layout, right? So what we generally have is we have a PMOS, NMOS, and on top we'll have a VDD and the VSS drawn for each of the standard cell, right? And so this particular standard cell will have a defined height. So, and whatever standard cell library you are picking, that will be coming up with a same set of height for all the standard cells in the library. So based on this standard cell height or standard cell library, whatever you are using, you will be drawing a standard cell rows. Okay. So what this standard cell rows does is it kind of used to place the standard cells in a structural format. So you're going to place all the standard cells inside each of these rows. Okay, and each of this row will carry a different supply. So for example, let's take an example that this is our VDD, right? And this is our VSS, right? And so first cell will sit here where you will have a VDD and the VSS, right? And so what we do is in the next row, whatever we create a VSS here. The reason is if you put again VDD here, then you cannot put anything here in between, right? So if you create a VSS here, what you do is you flip this particular cell, thus, and you can put another cell here, and this is kind of rotated by X, and you can have a VDD getting shared between this row and this row, right? So this alternative, we create a VDD and VSS rows in throughout all the power domains, okay? And so that you can pack 100% of your area with the standard cells, right? So this is what we call is a standard cell rows. And similar way, we need to create a metal track. So as I explained in the previous slide, each of this technology has a defined rule for the metal width, metal pitch. Pitch is the subsequent metal, how much distance you can draw between from one metal to another metal, right? So this is the pitch. So based on this technology rules, we create a track. So for example, and each of these metal layers are divided into horizontal metals and the vertical metals. So every alternative metal, say for example, M1 is a vertical, then M2 will be horizontal, then M3 will be vertical, M4 will be horizontal. So metal, each of this metal layer will be kind of opposite 90-degree flip by each subsequent layers, right? So based on that, you create tracks. So for example, M2 tracks you create, say M2 is horizontal. So what you do is, based on the technology rules, you create a virtual tracks, virtual tracks like horizontal tracks you create, and similar way you'll create a vertical tracks throughout your SoC. Please kind of apologize for my drawing, it's not good. So this each of this track will create, and this is something kind of you can use this track to route that particular layer. So for example, if you created M2 for horizontal and M3 for the vertical, right? So what you do is you can route all the M2s on top of exactly on top of this track. So, and why it's important is if you don't create a track, what will happen is if you try to draw somewhere here, then you cannot make sure that you are following all the spacing rule and all the connection rules, right? So if you have a proper tracks created, then M2 will be drawn exactly here and M3 will be exactly vertical. So you can drop a proper via here and you can follow all the technology rules, right? So that's the prime important for it. And so these are the two things we need to create. So this metal tracks and the standard cell rows are kind of a virtual. It will not be a physical, it will not be going to a foundry, but this is something to make tool understand that these are the things you can use it to place your standard cell and routes your signal. Okay, so these are the basic requirements to draw. Okay, moving ahead. So then, as I explained, so there are two kind of design. One is your IO limited, another is your core limited, right? So now, if you are doing the SOC level floor plan, you need to plan your IOs. So IO pad. So what you call is a pad, right? So pad is something. So whatever we see in the any IC or silicon, right? So what we have is a pins coming out of that SOC, it's silicon or the IC, and that is what we see outside is what we call is a package. Okay, and that package has a kind of SOC inside it or wafer inside it, and that particular the connection between your wafer to the package is happen through a pad. Okay, what we call is IO pad. So if you see any SOC and surrounded by all of you will have IO pads. And from this pad, you can say you will have some inductance circuit and some capacitor circuit. And then you can have your, this is your package. Okay, and package will have your pin out. So this your pins, whatever you see in the IC, right? So that will be your pin. And then this will connect to your pad, and from the pad, all the signals get transferred to the core area. Okay, so so what is the use of IO pads? That connects between your die and package, right? So this is your package and the die. So this connect between two, and it can drive a very big load. So generally, whatever we see, the loads inside each of this SOC is in terms of couple of transistors. But what if you see here, it has to drive a bigger load. So there is a bigger voltage shifting required when you kind of get out from the SOC and goes to the actual board level design. So you require to drive a very big load. So this level shifting or the voltage shifting provided inside the pad. And as it's big low level shifting, generally when you have a say 1 volt to 1.2 volt, it's a smaller level shifting. But when you shift from say 1 volt to 5 volt, right? So there is a huge noise need to be suppressed, and so if you there is even a minor noise at a 1 volt, it may lead to a wrong value prediction when you do a level shifting, right? So and so this require a very very high switching or very low switching noise for this switching between your one signal level to another signal level. And this is also exposed to the outside world, and so it can lead to ESD issues because we might be touching our hands to the pins of this your SOCs, right? So this requires very high ESD protections. So these are the functionality of the pads, and that has to be placed on the surrounded region so that all of your pins get exposed to the outside world. Okay. And yeah, so that's it on the IO planning. So, and based on the number of pads what you have, it can lead to a pad limited design. If you have so many pads that you need to increase this square area, right? So that will limit your SOC area by the IO pads. And but if you're limited IO pads, then it can be limited by your core area. Okay, so this is IO pad planning. Moving ahead is a partitioning of your design. Okay. So partitioning of design, first of all, why it's required. Partitioning of design, why it's required is, again, so putting our analogy of your house design, right? So you cannot have a full house without, if you are creating a bigger, say 24 square foot house, and if you're not putting any of the rooms inside it, right? So it's not much useful, and it may lead to not proper house. So similar way, any of your design SOC you are creating, right? So currently, whatever functionalities and whatever demand we have in the market, right? So each of these SOC may leads to hundreds of millions of gate size or the transistor size, right? And each of this EDA tool, which kind of we use to implement the SOC, has a certain limitations, and each of whatever the compute capacities we have to kind of apply to this tool and do the place and route, that also has the limitation. And as you move in the instance count increase, right? So if you go from say 2 million to 5 million to 10 million, then your runtime for each of this stage exponentially grow. Okay, and that will not be predictable results if you kind of implement the SOC as a flat. So what we do is we kind of divide the SOC into a smaller pieces based on its functionality. So first of all, what we do is we identify its logical hierarchies and try to divide it's based on discrete functionality. Say for example, in if you go refer to our first slide where you have uh, very kind of limited say 4 or 5 hierarchies, right? So each of these hierarchy has a discrete functionality, and it's only the interface between two hierarchies require a connection. So based on that, we identify these hierarchies and we kind of create a physical boundary around it, and then we implement each of these physical hierarchies individually in parallel. So what will happen is your design size has come down and the implementation has kind of gone serially to a parallel, right? So if you increase your instance count, your runtime is exponentially growing. But now if you have a smaller instance count in a smaller bucketized way, so you can have a very faster turnaround time, and you can kind of assemble the design at the end. So once all the partitions are implemented individually, then you kind of assemble all these partitions at the SOC level, and then you can kind of do all the sign off, and that can be your foundry ready SOC, right? So this is the prime important for the partitioning of your design. And so if you see as an example, right? So for example, this is our big design, and it has a various color coded module. What you see is each of this has a discrete functionality. So if you kind of implement with individually, that is, or the flat one, so it may lead to non-optimal implementation, and it can lead to a bigger runtime. But what you can do is, based on this functionality, you can divide it into each of the smaller modules, and each of the smaller modules you can implement. And even as the module goes small, right? So you can have a more flexibility to put a more time there and try to understand each design, and you can plan some custom ways to optimize better. But if it's kind of a sea of gate, right? So you may get lost, and you will not able to understand how is it going, how is it kind of fine tune each and every module to get it optimal, right? So this is very much important for partitioning the design, right? So now, once we partition the design, and it is the timing picture comes into picture, and we need to understand. Say, for example, let's take this isn't what we have partitioned, right? And if we have one flop sitting here and another flop sitting here, right? And there was a timing path between these two, right? So once you do the partitioning, right? So you need to make sure that each of this flop, whatever is sitting, so what we have done eventually is we have kind of cut down this path while implementing, and we have given some set of logic to this guy, some set of logic to this guy. Okay, and both of this has a different scenario now. Now to make sure the implementation, whenever we are doing for this partition and this partition, should see the real scenario in both the side, and it should not kind of screw up saying that it also does the non-optimal job this side, and this also does a non-optimal job this side. And eventually when you kind of assemble it and stitch it, you will have a non-optimal path, and this may lead to a timing violations, right? So how to do it, right? So for that, what we call is a budgeting and constraint splitting. Okay, so what it means is, say for example, you have a partition A and partition B, and partition C is your top level, right? And you have one floor sitting here, another floor sitting here. So, and let's take an example that from partition A to the boundary of partition A, you have a, say, delay requirement of 1. Between partition A to partition B, you have a delay requirement of 2, and between 2 to 3, you have delay. From this boundary of B to the floor inside B, you require a delay requirement of 3, right? And both of these say receive the same clock. So what we need to make sure is your delay of 1 plus 2 plus 3 should be less than or equal to your clock period, so that you can meet the setup requirement. I hope you have understand what is setup time in the previous session. So say in a way you need to make sure this 3 should be less than your clock period. Okay. And so what we do is, when you kind of split the constraint, or say you give the constraint to partition A, so what you see is you sum up the delay of 2 and 3, okay, and you say to partition A, saying that, so whenever you are timing this particular path, you account that you have already a delay of 2 plus 3 outside. Okay, so when you time the path from this flow to the boundary of this port, it will automatically add 1 plus 2 plus 3 when it times, right? In similar way, when you times the partition B, what you can say is, say your delay of 1 plus 2, you have to account when you time a path from this port to the flow, right? So this will also see the real picture outside, and this can, once you stitch it together, and what constraint it goes to see is saying that, okay, so you have a 1 cycle minus 3 minus 1 is your delay maximum you can take to route signal from A to B. Okay, so this is what we call a feed through constraint. And so once you stitch it together, you will automatically, if you meet the constraint whatever is given to each of the partition, then once you stitch it together, you will not see any surprise at the end. So this budgeting of the constraint is very much important during the floor plan. So when you do the partitioning, you also do the budgeting of your each of this design, right? Okay, moving ahead. So there is another issue once you do the partitioning, right? So as I explained in the previous slide, when we have explained the varieties of the floor plan, right? So for example, each one of the signal you have to travel through multiple partitions, right? So in the previous example, we have shown that this is traveling only through the top level. It's not going through any of the partition. Any question, guys? Okay, so if it's going through multiple partitions, say for example, this is our SOC and we have a partition A, B, C, D, E, F, okay, and the signal from D has to reach to the signal partition inside C. So what it can do is, it can say for example, we are taking a route through A, B, and C, right? So what it will do is, it will divide this path into a 4 segment, say D to A, okay, A to B, and sorry, D to B, A to B, and C to a flow. Okay, so then similarly divided into 4 pieces. Each of these partitions will receive these constraints, and this partition A and B will have a feed through constraint saying that and also it will see the extra port created inside that hierarchy. By default, inside the RTL, you will not have these ports, but while doing the physical design or the floor planning, what you see is there is a new port created because it requires to create a connection from D to C. So these extra ports getting created inside each of these partitions. Okay, and this constraint will be passed on to partition A and B, and when it implements, it's automatically have a port location saying that this location to this location you have to route a signal, and within this much time. Similar way, from A to B, you will have this to this, you have to route the signal within this given time. Okay, and so based on this, once you kind of stitch it again, you will have a proper timing and you will not see any issue at the end. Okay, this is what we call the feed through planning. Okay, moving on. What we understand is we have created the proper area. We have created the power domain. We have created the partitions. We have kind of punched the feed throughs throughout it. Now let's move inside the partitions. Okay, so say for example, you have partitions and it has many of the macros in it. Okay, what is macro is? Macro is generally a pre-implemented custom plan design, like memories, what you have, like a PLL or in any other analog blocks, right? What you require. And so in short, whatever the design that can be a modular, what I mean is it can be implemented once and you can kind of call it out multiple times. That can be a macro. And this can be a configurable as well. For example, if you wanted to create a 2 MB of cache inside your processor design, so one way is either you can create a 2 MB of bigger memory, or you can create a very small memories, say right 128 KB, and then you can replicate that memories multiple times to create a 2 MB cache, right? So important. So why we create this is because if you use a bigger memory, you will have a bigger access time and you cannot meet the setup or you cannot meet the timing. So if you kind of create it a smaller memories, right? So you will have a better timing and you can have a accessibility as well, right? So that you replicate multiple times inside your design and you use it as a macro. So this is a macro, right? And each of these partition can have a 0 macros and it can have a few hundreds of macros as well, right? So that's purely based on its functionality. Each of these macros are pre-implemented, as I explained. So it will have certain resources consumed from our available resources. So for example, if you're using a 10 metal layer process, right? So each to implement this macro, the user might have used certain layers to implement it, right? So those layers are already been consumed inside macro. So when you kind of use this macro inside our partition, you will not able to route any signal on top of that macro with those layers, because those layers are already been consumed by this particular partition or this particular macro, right? So you will have a blockage of that particular layer on top of that macro and you cannot use it. Okay. And so generally what we do is in the macro placement, we try to understand the connectivity of the macro, and based on that connectivity we group the macro very first, and we try to push the macro towards the boundary, because any of the cell, if it sits in say in this area, right, and it has to talk to another set of cells which sits in this area, it has to cross this macro multiple times from here to here and from here to here, and there are already many layers blocked inside this macro, so it may create issues to kind of jump over the macros and can leads to a congestion. Okay, so what we do is we kind of throw these macros inside the corner so that all these standard cells try to place in the core area, and it don't require to kind of jump over the macros and kind of create issue for the congestion. Okay, so these are the before we start placement, we need to make sure that this all are placed inside the floor plan stage. And also all of these macros have a set of power pins which need to be connected, and that will be covered in the power planning phase. So this also require a floor plan touch. Okay, hope this is clear. Now let's move on. Okay, so once you done the macro placement, then comes the physical cell insertion. So what is physical cells? Okay, so physical cells are the cells, those are not having any functionality in it. Okay, discrete functionality in it, like AND or NAND, what we have gates in the libraries. These are not a logical gate. Its purpose is only for the physicality of the implementation, right? And it only helps in the kind of fabrication, testing purpose, and the better implementation of your silicon inside the foundry. So this physical cells also is one of the requirement from the foundry perspective, right? And also from the semiconductor perspective. So let's try to understand what kind of physical cells what we have. So yeah, any question? Okay, so what we have is end cap. So end cap is generally inserted at the row end. So for example, if you have drawn the stand cell row here, and you have a NVL, if you put the stand cell here, right? So you will have an NVL and the P substrate. And so to proper, if you leave the last cell here somewhere, right? So you need to have proper NVL enclosure at the end of each row. So for making this, you put an end cap cell. So you have end cap cell sitting on both the side of your rows, so that you can have proper NVL enclosure. You have a tap cell. So tap cell is, I think all of you might be teaching this to your students, that for preventing latch up, we use the back bias to control the latch up, right? So latch up, to controlling the latch up, we use the tap cell. The purpose of tap cell is kind of providing a bias inside your back bias inside your core area. So we distribute this tap cell with regular distance throughout the core area, and that can supplies to your silicon, right? So back bias to throughout the core area. So this is the practical use of the tap cell. ESD cells, we use it for the ESD protections. There are certain marker cells that are used for the kind of alignment of the wafer on the fabrication time, right? So that kind of marker cells, we use it and kind of distribute it with based on the foundry rules. And there are few process sensor cells. So process sensor cells are used specifically to kind of, if you are fabricating one full wafer, say 12 by 12 inch of wafer inside the foundry. And what will happen is your doping concentration and your each of the silicon characteristic throughout this 12 by 12 inch of your wafer will not be common, right? It will have somewhere you will have minor increase or decrease in doping, and your characteristic of silicon will be varying. So whatever the fabrication you do, right? So this will, each of this part of your wafer will have a different process variations, right? So what we do is we kind of distribute the process sensor cells inside each of the some, so with every regular distance. And after fabrication, what we do is we kind of pass it the current through it and try to see how much time it has taken to kind of travel this cell. And based on that, we measure the quality of the process, saying that this is my fast process, this is a slow process, this is the typical process, right? So based on that, we try to identify that how the silicon implementation is there inside the foundry. And these are the sensor cells used for the process sensing. Also for the low VT, high VT, and the standard VT, how the variations is there. So all these are used for the process sensing. So these process sensor cells are used and distributed throughout the design. So all of these cells, if you see, right, so those are not having any logical functionality to kind of give as an output, but these are used for the only physical purpose, right? Right. Moving ahead. Now it comes to the power switch. Okay, so power switch, as I explained in the previous slide, so I'm trying to just move fast. Looks like running out of time. Power switch are kind of a, it's bigger transistor, you can assume that, where your drain and source are tied to one side and gate is sourced to your VDD, right? So when or gate is sourced to, sorry, I missed it. So your gate is connected to enable, and it's a bigger transistor which can carry your current, right? So and your, say for example, your drain is connected to your VDD, and your source is connected to your transistor. So what will happen is when you get enable signal, your power supply will be shorted with your transistor, right? And once you kind of disable the enable supply or the gate, what will happen is your power will get disconnected from the transistor. So this is a very bigger transistors in a way, which is used to, which can drive the very big current to fulfill the need. So power switches are distributed throughout the gated domain, where we wanted to shut off that domain, and this are kind of connected between the power rails and the transistors, right? So this can be used. So there will be enable chaining done between each of these power switch, and generally this is in a daisy chain form or another chaining format. It will not be kind of a broadcast way where all the power switch can enable in one point of time. So if you, what will happen is, if you enable all the power switch in one shot, what will happen is it will drain a huge amount of current. It will enable all the logic in complete area in one point of time, and that will drain a huge amount of current from the your VR or the power supply, and that can lead to a high crowbar current, right? And this may kind of damage multiple things, right? So and to save from it, what we do is we do a daisy chain and we enable power switch one by one, so that you don't have a huge current sink from the source, and the supply, all the core area get enabled one by one. Okay. And so this is the use of power switch, and power switch only inserted during the inside the gated domain, and other power domains generally don't require a power switch. Power switch can be two types. One thing is what I've shown here is the distributed power switch, where you distribute this power switch throughout the core area. Another set of power switch, what we call is header power switch, which generally what we do is we try to put that header in this say boundary outside of the core area, and from this switch supply only kind of get it inside the core area from all the side, and this get used inside for this cell. So the only parts will be surrounded by area, and there the switching happens based on enable, and then it supplies the gated supply to this core area. Okay, so these are the power switch. Okay, now so I think hope this is clear till now. So okay, now let's go to the PDN. So PDN is something like electrifying your house. Okay, so PDN stands for Power Delivery Network. So PDN is prime and very much important for the floor planning task, where you kind of actually draw your power and connect these power supplies to, how can you connect each of this power supply to each of your transistors, right? And this plays a very big role in overall functionality, overall kind of reliability issues of your silicon, right? And so generally, we as explained, so for example, if you're going with a 10 metal layer process, so you'll have a stack of 10 metals from say M0 to M10, and the highest metal layer generally get connected through a C4 bump. So it's a C4, it's a bump layer, right? So, and it is a bigger metal piece, you can assume, which is distributed throughout the core area. And from this bump, it will get the supply to say M10. And from M10 through multiple stack vias, you kind of supply this current through till your transistor. Okay. So non-optimal PDN design can lead to multiple issues, right? So this can be your EM, your BTI's bias temperature inversion, your static dynamic drops, right? So lots of issues can arise because of it. And now how to choose proper PDN, right? So for that, what we need to understand is, understand first of all your design need. Okay, so each of this module, whatever you have planned to integrate inside given SoC, each of, based on its functionality, it will have a certain set of power requirement, right? So for example, if your power requirement is give me a second. If your power requirement is say 1 milliwatt, or say or sorry, if your power requirement is 10 watt, right, for each of the one module, right? So then what you need to do is, so you kind of sum up with all the modules whatever you have, and you come up with your total power needs. So this much power I need for my given technology, or this technology or this functionality, I need this much of power. And based on that, what we have is that each of the SoC will be operating in certain defined voltage. So say, for example, if you're working on 1 volt, right, 1 volt. So if you have a power, if you have voltage, then you can come up with your current need, right? So your P is equal to VS, so you'll come up with your, this is my current requirement. So based on that current need, each of these metal layers, whatever you're using, that has a certain set of resistance defined for each of the layers, and per micron. Okay, so per micron intersection, each of the layers will have a per micron intersection, each of this metal will have a certain resistance defined, And based on this resistance, you can calculate that how much of current it can carry, right? So you have a voltage, you have a resistance, you can calculate the current it can carry, right? So based on your current need, what you have, you can draw a parallel metal such a way that your total resistance come down and you can meet the current need, whatever you have for your SOC. Right? This is the simple calculation what we have, and so once you have identified that each of these metal layers need to carry, say, 10 milliamp of current, and then you come up and you have a resistance of each of these metal layers, so you come up with this much parallel metals I need to reach to given transistors to supply this much of current. Right? So, and based on this calculation, we come up with pitch and the distance what we require for each of the VDD supply, each of the VSS supply, and then we draw metal stripe from the top to bottom. Okay. Yeah. So to measure the kind of your criteria of the PDN, I think this is what I tried to explain you previously. You need to understand the design needs, come up with the resistance property, and come up with the total current need, right? Now, so I think this is what we have in the floor planning. And so how to measure your quality of best floor plan? You need to have optimal shapes for your each of the partitions and your SOC, which can hits the best PPA. Quality of power delivery, which should not give any of the IR issues. Proper pin placement for your partitions, which can be optimal for all the physical need. Your base DRC means your all the Foundry rules are met, right? And whenever you are creating a partition, you should have quality collaterals for your child partitions so that it can have proper implementation. So this is the quality of the floor planning what we measure, right? So okay, so this is what we have in the floor plan. Now let's understand where we are. So what we have is we have done the very beautiful floor plan, and sorry, any question? Okay, so we have done the very beautiful floor plan. Now we have, I think, let's understand that we have gone through a synthesis flow as well, where based on this floor plan, you have an optimal synthesis where you have done a proper optimization of logic and you are meeting the timing and based on this physical constraint, right? And we are moving to a placement stage. So what is placement? Okay, so placement is a process of giving location to each of the standard cell in the rows created during the floor plan. So we have created a standard cell rows. Now we need to place all the standard cells inside those rows, and which results in the optimal area, congestion, timing, and power, right? So these are the what we call is a PPA, or what we call is a metrics which we need to measure, right? So which can give us the best result out of that placement. Right, so this is the overall placement philosophies, and let's go and understand what each step what we have inside the placement, right? Right, so placement steps involves, so first one is a pre-place. I'll go through each of these in detail and try to explain you what it is. So once we do the pre-place, then the initial placement and legalization, then the pre-clock planning. So if you generally see this one, right, so or flow, we have a CTS steps after the placement, right? But this is the another thing where we wanted to make sure that whatever optimization steps we run, whenever we start the optimization, we have all the pessimism related to future changes kind of mitigated inside this stage. And for that same purpose, there is also some say of clock tree synthesis at the placement level, which I'll try to cover it here. Okay, and then the high fan out synthesis we do, then the optimization we do. There are multiple optimizations. We have timing, congestion, power, area, right? So, and these are all the optimization, and then we deliver the quality output at the end of your placement, right? So let's first understand what all are these steps. So let's understand what is a pre-place. So pre-place is something, it's an optional step, first of all. Okay, pre-place is something before you give your floor plan or the synthesis netlist to your placement tool. You are having a flexibility to do some customization so that your placer tools does the right job or a better job, right? I would say, right? So and for the same purpose, what we do is we kind of do some customization, which can help in overall design convergence, right? And this customization can include your anchor buffering, and okay, this customization can includes your anchor buffering. Uh, so what is anchor buffering is your boundary. So I think till now we were covering to both the floor planning for the SOC level as well as the partition level. The placement is mainly concentrate around the partition level optimization, right? Once you kind of come out of your uh, uh, partitioning design, so you are implementing now each of the partitions, right? So what is anchor buffer? So anchor buffering is something like, for example, if you have created two partitions inside your block, right? And say one particular your port is connecting here to here, and it might possible that this signal, once it exits the partition, it may have to travel a longer distance to reach to another partition. So what we do is we kind of put a anchor buffer on mouth of each of the partitions. So this buffer is kind of a driver which can drive a longer distance. If you don't have a buffer, the signal can go weak, and it can lead to many other transition issues or the weaker drive at the output of this one. So what we do is we bump up its level such a way that transition such a way that in the mouth of each partition, and so that it can travel a long distance. And even if you don't have a visibility what is happening outside of your partition, you can kind of uh, get prepared for any worst scenario, right? So that for the same reason, what we do is we do anchor buffering is for all the ports which is entering and exiting from this partition. Okay, and similar way anchor buffer we can do it here, so that whatever, even if you are getting a weak signal, it can boost up in the mouth of the partition itself and can have a proper timing after this. This is what we do before we start a placement, so that when placer sees it, sees the optimal optimization here. Next is defining the custom routing rules for the clock. Clock specifically, I think in the next session of the clock tree synthesis, you will be able to understand what is the NDRs and what is the non-default rule for the clocking. So if you are doing some clocking related stuff here, you need to understand that clocks require some custom things. So clock cannot be routed as it is as a signal, because clock is a critical portion of your digital design. And if you see any disturbance inside the clock, that may lead to your setup hold issue, that may lead to your many glitch issue, or it can lead to any other issues, right? So you need to specifically define the proper routing rules for the clocking. You need to make sure whatever signals you don't want to buffer it, whatever signals you don't want to touch it, right? For example, some of the say for example, there is one analog signal traveling on top of this both the partitions, right? So and there is no analog supplies available in this area, so you cannot buffer it here ideally. So you need to make sure that this particular net, whatever it's going through this partition, should not be buffered by the place and route tool. So you need to give a don't buffer attributes for all of these nets. You need to prune your science libraries so that you can have a better power, area, and performance. So in the libraries, generally, you will have all the varieties of the cells. It can be optimized better for the power. It can be optimized better for the performance. So it can have various VT flavors, like a lower VT, it can be faster. Your right, and higher VT, it can be slower but better in terms of your leakage and the total power. So based on that, we choose right varieties of the cells, and we block all the unwanted cell from the library, and we say that to a placer tool, saying that you use only this set of cells while optimizing, so that I can get my best whatever I wanted to area, power. Yes. Okay, another is adding a spare cell. So spare cells are generally used during the metal ECOs, right? So for example, if you have implemented your SOC, you have given it to a foundry, you get your SOC back, and you somehow you realize that, okay, there is some bug which I require to fix it, right? So now, so in the foundry, the fabrication happens layer by layer. So if it is possible that you can fix that particular bug with only some metal changes, right? So in that case, also if you require some add some flop or some, guys, can you please mute if you are not wanted to speak? Okay, yeah. So if you wanted to kind of use this cell after fabrication happens, right? And if you wanted to have some ECO to be done or some change to be done inside your functionality to meet or to change it, right? So based on the need. So what you can do is you can use these spare cells inside your design, and you can connect that spare cell to create any given functionality or ask functionality. And so what benefit you will get is you will not have to again refabricate all the bottom layers if you are using the cells. So that means your till M0 or till your poly you have already fabricated, and then you are only changing after your poly. So you can use the same mask or same layers whatever you have till M0 or till the poly, and then only the above layers you can refabricate so that you can save the cost of your SOC or refabrication, right? So the spare cells are used for doing the metal ECOs, right? And the defining placement and routing blockage based on your prior runs or design needs. So if you wanted to say somewhere you are seeing you want to have a lesser cells to be placed, so you can put a placement blockage, say that in this area I wanted to only say 20% of the cells to be placed, remaining everything should be outside of this area. So this can be based on the need, you can try it. Okay, so these are your um, uh, these are your custom requirements. You can give it to a placer tool before it starts the placement, right? So in the initial placement and the legalization, what it does is, as of now, you don't have any cells kind of thrown inside your core area, whatever partitions you have created. So placer tools, first of all, what it does is it tries to analyze the connectivity. So you have a pins placed on your boundary. There is a set of pins coming as an input. It does some functionality, it goes to another module, does some functionality, then it goes to out, right? So based on this functionality, tool tries to understand how is the connectivity is there, and based on that, it approximately throw each of the module to appropriate location. Okay, and all the modules will generally be grouped together in the initial placement. Okay, and then it tries to analyze the timing. Okay, if I kind of throw this module and place it something like this, whether it will meet my timing or not, if it will meet my congestion or not. Okay, it will see any issue related to optimization. So once it does that, what it does is then it kind of does the refinement to meet the timing and congestion picture. So first it has thrown the cells, then it will do a refinement to whether by refining that, some minor correcting that, whether it can meet or not, right? So then it does that refinement, and then it goes to the legalization. So legalization is step where each of the standard cell, wherever it's thrown inside the core area, it the placer tools gives its a legal location. So what does the legal location is? So for example, if you see the course placement here, right? So tool has tried to throw, so you understand each of this color is a different module. Tool has tried to throw each of the modules to a different location based on its connectivity. But all of the cells will not be legally placed inside the rows, whatever we have created. So once you fine tune it based on the timing and congestion, your legalizer will tries to legalize it to each of the nearest location to those cells on the standard cell row. Okay, and it will also does the operations of like what we discussed, the flip, right? Flip by X to make sure a VDD and VSS gets aligned to each of the each of the placement rows. So this is what the legalization is, right? Now, pre-clock planning, right? So what's a pre-clock planning? So if you do the placement, right? So in the placement step, what we do is we kind of throw, or we kind of place each of the flops, each of the modules, and standard cell of it, right, in the core area. And generally after that, the clock tree synthesis happen. But what is the drawback of it if we don't account the clock tree planning very early in the placement? So in that case, what will happen is, so for example, if some area where you have a higher amount of flops are sitting, and you don't have any space to kind of place newer cells, And in that point of time, when you have to kind of say, let's take an example, right? So let's take an example. Say you have a flop sitting here nearby each other, right? And like this. And if you all of this clock, it will have a clock, right? So it will have a clock pin to get it connected. But if you don't get a enough area here to connect its clock, right? So what will happen is somewhere in your clock tree synthesis, you will have a one set of clock driver sitting, which will drive all of this here, right? And this may lead to unoptimal clock tree synthesis. So what we need to do is we need to reserve some space for all of this clock cell inside near to this flop area, so that when you do a clock tree synthesis, you have that cell can be accommodated here, and that all of the clock pin connectivity can be better, right? So one is similar way for the routing resources as well. So when you have so much cells placed here, your routing will also be tight here, right? So you'll not have enough space to route. So if you reserve some tracks for the clock tree, that will give a better clock tree results once you do the clock tree synthesis, right? So make sure enough routing resources are secured, and preferred location for the clock cells are secured, and also based on this nowadays, so it tools in the placement time itself, it calculates how much delay I'll take in my clock tree for reaching to each of the flop. And based on this this value, it annotated the delay to each of this flop and does the timing optimization, right? So this is what we call early clock synthesis. So and that helps us to see the real picture, what we are actually going to see after the actual CTS, right? So the tool will try to understand all of these needs, and it can do the better optimization in the placement. Okay, now how to do it? So how to do it? You need to define a proper non-default routing rule for the clock. Okay, you need to define a proper clock constraint, right? So how many maximum load each of these clock cell can drive? What is the maximum length of each clock net should be there? What are the varieties of the cells, clock cells I wanted to use, right? And any clock cell placement, so you want to give some space between the clock cell to clock cell for the IR issues. I'll explain what it is. And then useful skewing. So useful skewing, generally what we use it when you have a one path from one flop to another flop, right? So what you do is if you have a margin in from this to this path, and you are tight in terms of timing here, then what you do is you push this particular flop, you give a more delay to this flop, so that you can have a more time to meet this path, and you can borrow this particular time from next cycle, right? So that you can have a proper timing here and you can meet it. So that also you can use it in this stage. Okay. So this is what pre-clock planning. This is a set of constraints we need to give it to a tool, and tool will able to understand and analyze it and start its pre-CTS activity in the placement stage itself. Okay. Now moving to high fan out net synthesis. Okay, this is very much important part of your implementation. So what is high fan out net synthesis? So fan out is simply a number of gate connected to each of the output of a particular cell, right? So for example, if you taken this as this AND gate as an example, it has a 6 AND gate connected output, so its fan out is 6. Why we need to do high fan out synthesis? Each of this particular cell will have a transistor inside it, and say for example it is connected to its gate, right? So each of this gate will have certain set of capacitance, and this net, whatever we are routing, it will have a capacitance of its own, right? So whenever the output of this guy is driving this transistor is driving all of this transistor, it has to charge this net as well as the gate of all of this one, right? So it has this limitation, limited driving strength available for each of the transistor. So if it has to charge a more capacitance eventually, then it will take a more time to charge it to a given voltage, 7P0, 1.0 volt, right?
and it may kind of increase its delay. It may also deteriorate the signal. So many times it happens is even if load is so high, it may not able to charge it at that point of time. It will not reach there. It will be a glitch. You lose your functionality even, right? So what we need to do is we need to make sure that each of these cells are being characterized inside standard cell library to drive certain set of load, and that particular load is given in the library. So what we need to do is we need to make sure to meet that load, we divide its fan out. And what we have done here is, for example, this particular AND gate has its fan out is kind of buffered. So these two AND gates has been buffered by this buffer, and these two AND gates is buffered by this buffer. So now this particular AND gate has only 4 fan out to drive, and this signal is getting pushed and buffered here, and it will have only 2 fan out to drive. So eventually everything win-win, right? So this is what we call a high fan out net synthesis. And during this high fan out net synthesis, by default tool exclude all the clock networks and everything, because clock is also a high fan out, but because your clock pin will be driving all the flops inside your design, but that should not be synthesized or buffered here. That has a specific step in the CTS, right? So this is what we call a high fan out synthesis. Okay, moving on. Optimizations. Okay, so these are the various optimizations happens during the course of placement. So we'll try to understand each of this, what it is. So let's first of all go with the timing optimization. So timing is something setup timing, what we fix in the placement stage, right? So, and hope you have understanding of basic what is setup timing. Setup timing is a flop to flop timing. So one data is launched from one flop and it has to capture in the next cycle by the next flop, and tool tries to optimize it. So this design optimization can be multiple things. So for example, this is one flop, and you have one logic, second logic, and likewise you have multiple logic which is driving to a flop. All of this is connected to a clock, right? So so what tool does is first it's time it, and we see whether your total delay from this one till its time reach here is less than your clock period or not. But if it's more than its clock period, then it tries to do multiple things, right? So it tries to change this cell. So if you have a bigger cells available, right? So here then it can have a lesser delay. So and then you can swap it with a bigger drive strength cell. Another option is you can change these cells to a lower VT cell, so that you can if its VT is lower, it can get enabled very fast, and you can have a lesser delay to get it enabled, right? So you can change it to a lower VT cells. That will also reduce your delay of each of this module. And by this, you can kind of reduce the total time from the slope to flow. Okay, and then you can meet the setup timing. There are certain soft checks also need to be fixed. Any of the bigger transition you are seeing after even the max fan out, then you can. So for example, this particular guy is driving multiple fan out. So what you can do is you can size this particular cell to bigger cell, and which has a better W/L ratio or better the driving strength, so which can drive the more load, right? So that's what you do, right? So this is what we do as a part of timing optimizations. One is what you call a setup fix, another is soft check fix. Soft check means your transitions, your fan out, your load, your any non-bufferability related things. All of these things you do as a timing fix. Okay. Moving on. So another optimization is what we call is congestion optimization. Congestion can be two types. One is called a placement congestion, and there is a routing congestion. Placement congestion is when you have a design where only available area is more than your logic area, right? So if you have more standard cell to place and your total area available in your silicon is less, then you encounter a placement congestion. So tool will try to throw the cells outside somewhere, and you need to understand how can we fix the placement congestion. So and it could be reason of your floor plan area given is less. It could be reason of your bound is something like you give a tool a guidance saying that this particular module has to be placed in this area only, right? So this is something like bound, right? And another is a tighter constraints which leads to cell clustering. So for example, if you give a very high transition limit, say, then what
tool will do is tool will try to do so much of buffering to meet the high transition need, and this will boost up or this will blow up your number of instances in your design. So that will also leads to a placement congestion. Another congestion part is a routing congestion. Okay, so routing congestion is something like, say for example, if you have placed your standard cells and you need to connect each of the standard cells input and output pin to based on its connectivity, right? So what will happen is, so some places it might possible that say, so let's take this as an example, right? So this is the set of AND gates we have, and in this area somehow if you see, right, so there are so many routes are passing through it. Each micron inside the physical design what we draw, it has a limited set of routing tracks available to route each of the metal pieces. Now, if your number of wires you have to route in given area is more than the route tracks available, then it will create a congestion. So what tool will try to do is, tool will first try to throw this signal and it will try to detour it. Say, rather than routing it through here, if I can route through here, that will also work. But what problem it will take is, it will have to travel a bigger distance, and hence a bigger delay it will encounter to reach from one place to another place. This can be lead to a bad timing, right? And another option is, if you restrict it to don't detour it, so tool will even try to route it here, and it will create a shorts. Short means it will go out of capacity and try to route it. So when you see this one, tool will see that, okay, I had a limited space. I try to do my justice to route this, but I still left with this many overlaps of the routes, right? Which cannot be fabricated. So you need to fix those overlaps and fix the routes, right? So that's what the routing congestion is. Okay, so what could lead to a routing congestion is your bad floor plan, bad macro placement, right, and pin placement. So if you have kind of placed macro such a way that it has so many signal has to cross over that macro, and it may lead to the congestion there, right? Because there will be limited space over the macro, as it is already consumed many of the routing layers inside it. Non-optimal placement, that means your tool has done the injustice and thrown everything inside one corner of the area, and it has so many routes to route only in that area, but other area is empty, right? So that's non-optimal placement. High standstill density, you have so many standstill packed in one area, so each of the pin of that standstill has to be connected, so that if you kind of have a sparse density inside your core area, this will lead to a better routability as well, right? And high buffering to fix the DRL, which I already explained. And so these are the congestion issues what we see, and the tool does the various optimization inside its algorithm its own, where it tries to fix all of these issues by its own. It tries to kind of throw the cell away from each other. It will try to detour the nets. It will try to fix the timing on that net. It will try to reduce the densities, right? So, but it will not do the macro placement again. These are the whatever the things we have done as hard-coded things, right? So that has to that will stay as it is, and that could lead to these issues as well. So before we give all these hard constraints, we need to understand that what will be the implications of it. Okay. Moving on, power optimization. Okay, this is very, very much important or a very, very crucial part of recent technology and the recent need of all the industries. Okay, so as our technology is shrinking, we are very limited with the area, right? We are limited. So even if you supply a voltage, but your performance will stay as it is, and you are tightly packing more and more number of transistors in given area. And because of it, what will happen is the power consumption within this given area is massive, and it's not scaling down as we are scaling the technology, right? So to reducing the power with scale technology is very much important. And so for that, there are multiple techniques involved in power optimization. Okay, so I'll try to cover up, touch based on few of these. One is the right VT selection. VT is your threshold voltage, and if if you have enough margin in your timing, right? And what we would do is we should always use a higher VT cells in the paths so that your leakage contribution to the design will massively reduce. And if your timing is meeting, so use so that you have less leakage overall. Tool does the area recovery. Area recovery means again, so wherever you have bigger cell present and it's just no need to drive a bigger load, and it can meet the timing with a smaller cell. So it will try to reduce the W/L ratio, and it will try to choose the smaller cells from the library, so that its area will also reduce, its power consumption will also reduce, because smaller cell will have a lesser number of transistor and lesser number of power requirement, right? Wire length reduction. So so one of this is a scan reordering. So scan insertion happened during the synthesis, and so scan reordering is something like the scan chains, whatever you have drawn or connected throughout the flops, right? So you reorder it such a way that based on your placement of the flops, like let's take an example. You have one flop here, you have another flop here, third flop here, fourth flop here, right? So you have connected like a scan chain like this, where your scan is going there, then again coming back here, and then again coming back here, right? Or again say here, right? So, and then it's going back here, then again coming back here, and then again coming back here, like this it is doing, right? So if it's doing like that, then what you could do is you can kind of rechain it such a way that you can kind of make sure your local connections are happen first, then it goes to out, and then it goes here. So you can have a lesser wire length here. So if you have a lesser wire length, then it means you have a lesser metal is eventually a capacitance, right? Lesser capacitance to charge and lesser power consumption, right? So that scan reordering will help to reduce the power. Overall wire length reduction in the design will also kind of reduce the power if you kind of reduce the distance between the cells wherever it's possible, and reduce the metal length. So that will help you to reduce the power. Activity-based power optimization. So this is a need of an hour for all the industry now. So activity-based of each of the module, whatever you are implementing, right, that has a certain set of use case, right? So for example, if you are doing the DSP processing, right? So you have a use casing that this is my numbers or the workload is coming. I'll do the DSP operations, any of the DSP operations on it, and then I'll have a certain set of output, right? So based on that, each of the RTL team or the architecture team come up with some workload saying that, okay, this, if you give this workload in this particular scenario, this will operate at maximum throughput and this can consume maximum power. So what we do is we take that activity and we annotate that activity to that module inside physical design, and we simulate it inside here, and then tries to understand that, okay, this module is taking power, this much of maximum power, and now how can we optimize further? So let's take one of the example, right? So for example, this is my AND gate, and this is my, say, flop, right? And this is from flop, this is going to another AND gate. What I'm saying is this particular AND gate to this particular flop, right? It is having a maximum activity in given scenario, and this particular thing has a very less activity in this given scenario. So what I could do is I can move this particular AND gate very next to the flop. Okay, what it will do is it will reduce the length of this metal as it is having a higher activity. So each of the time it has to charge and discharge this particular net, and if required, I can move this guy to away. So because it's having lesser activity, so its charge and discharge will not dissipate more power, but charge and discharge of this particular metal length, metal net is going to take more power. So I'll move this particular AND gate next to the flop, so it will reduce. I think this will not able to cover in this time, so I'm just giving you as an overview here. Another is a multi-bit conversion. So multi-bit conversion is something like, for example, you have a 16-bit or 8-bit bus, right, is coming
here, and all of this have a going to a flop, individual flop, and all of this flop have a common clock connections, common reset connections, right? So there are two options. One thing is we can choose the individual cell from each of the libraries and implement it. Another could be, so library generally have come up with a one single implementation of the flop, which has 8 flop inside it. What we call is a 8-bit flop. Okay, so this 8-bit flop has a 8 D pins and one clock pin, one reset pin, one scan in pin, okay, and 8 Q pins, right? So what it does is, so this will be customly optimized such a way that its total area will be quite less than the 8 individual flop. Its total power will be quite less than the individual flop, and it will have a lesser connections, because if you choose individual flop, each of this clock pin of this flop has to be buffered and connected properly, right? Here you have only one pin of the clock which will be driven, and area is less, your power is less. So what you can do is, wherever it's possible inside design, tries to choose multi-bit flop rather than the single bit flop. So this will also help you to reduce the area and power. This is the kind of a set of power optimization techniques what we have. And another is very important is what we have is IR drop challenge. Okay, so or the reliability challenge what we have. Okay, so again, with the scaling technology nodes, your area is getting reduced, right? So with transistor, and as your area is reduced, your metal width is also going to reduce. You have to route more number of metals inside given area, right? So you need to have a choose a lesser width in the metals, whatever you're routing. And because of it, your width is reducing, your resistance is definitely going to increase, and that has created a huge challenge for the power delivery, specifically what we have it, right? And this could lead to many of the issues what we see is static drop, or as I explained, the PDN challenges what we have, right? IR drop issues what we have. So there are various techniques Placer tool specifically plays to optimize the IR drop issues or the PDN issues, right? So one thing is what it does is high activity cell declustering. So what it does is, so once you annotate the activity, as I explained in the previous slide, so you annotate the activity, then it tries to understand, okay, which particular set of cells are active in a given point of time, given timing window, right? Then what it does is it decluster it. So within given time, if your so many cells are active, right? So what will happen is it will sink more current to charge and discharge at the same time, and that will have a challenge in supplying current to that given area. And if you decluster it, if you move all of these cells away from that centralized location, what will happen is your current sink requirement will be distributed. It will not be in the one place only, it will be in the different place where you have already a parallel stack supplying current from the top, right? So your current demand can be parallelized by declustering of the highly active cells. This is one. Another is called a slack-based deskewing. So slack-based deskewing means, for example, if you have continuously 2 flops switching at the given time, right? So this is one flop, another flop. This both the flops are connected to a same clock, and these are switching at the same time, and this is consuming more power. So what you can do is you can delay this flop if you have enough margin available on the next stage. Okay, so you can delay this clock of this flop. What will happen is this flop's clock will delay, and so say this is your time t where you are kind of seeing more activity. So if you delay this one, what will happen is this flop will move at t plus delta t time, right? So your flop will move here, and your max power requirement within this window will get shifted, right? So eventually you are reducing the peak from here by shifting some of the load to a next set of timing window, right? So this deskewing specifically help in terms of the IR drop reduction. Clock cell selection. So clock is a prime and very much important component in your power consumption, because your clock
inside your design will be 200% toggling. That means whenever you are kind of, if you consider this as a one cycle, right? So for each cycle, it has to charge as well as it has to discharge, right? So 2 times it has to toggle. So in given cycle, it's 200% toggling each of the cells inside your clock tree. And wisely selecting the proper cells for the clock. So what we can do is to reduce the clock latency, many times we choose a bigger cells. We can choose the very low VT cells, right? And all of this we can do it. But if you don't choose all of the cells wisely, and you know that each cycle it has to charge and discharge, this can dissipate the maximum number of power. Okay, and so we need to wisely choose the clock cells, whatever you're using for your design. Selective power stripe insertion to fix the IR drop issues. Okay, so and IR drop. If you are seeing in, say, for example, this area, you have a higher power drop, right? And you have already drawn your powers with certain intervals to supply to your transistor. You're seeing a more drop here. So what you could do is you can incrementally, if your routing resources are available, you can draw extra stripe here to supply a current from the top level, so that you can have a parallel resource and your resistance will reduce and you can supply a more current to this area, and this can meet your IR need, right? Another techniques what we use called a decap insertion. This is a decoupling capacitor. So decoupling capacitor is nothing but this is your gate. Please pardon for my drawing. What you do is you short this to guy, right? And you have a very big cap in this one. So what will happen is, in this cell, what you do is you insert between your VDD and VSS rail, whatever standard cell row, whatever we have created, right? And so what it does is, say, for example, you have a cell sitting next to it, and this particular cell is encountering the IR drop issue. What it will do is, so when it's not having the current sink, tool will kind of charge this particular capacitor, okay, and it will store this charge here. But when there is a need of higher charge to this particular cell, and if your supply is not able to sustain that and it sees the drop here, what it does is this can discharge through here, and this can support this particular cell to maintain its voltage level. So what we call is a decoupling capacitor, and these decoupling capacitors can be added throughout your design wherever you are seeing this IR issues, right? So this can locally help. It's a smaller capacitor which can locally help to boost the rail for a small moment of time, right? So this is what we call as the decoupling capacitor. Okay, yeah. So these are the various techniques we use to kind of reduce the IR drop, and yeah. So I think that's on the placement. So these are various techniques what we have in the placement side. And so just to summarize the thing, right? So what we need to do is we need to, in the course of placement optimization, we need to make sure our design area is as minimum as possible, wire length as minimum as possible. There should not be any overlap of the standard cell. All the standard cell has to be placed evenly. Your timing should be clean. Whatever the constraint you are optimizing, it should be clean. Your congestion should be clean. Your power is as minimum as possible. You should not have any IR issues, and your clock resources is best as possible. So in a way, if you kind of understand, if you consider this as a multi-dimensional vector, right? And if you try to put it in multi-dimensional vector, and what our goal is, we need to reach to the global minima, and which will be the best for all of this one. Okay, and that is what is an ideal placement is. Okay. And generally, many times what we do is we end up with a local minima where 1 or 2 or 3 vectors we end up with the best, but some other vectors can be not optimal, and this could lead to many challenges. So choosing the right value overall and to choose the to reach the global minima is very much important for all of us. Okay. Yeah, so that's what I have for today, and I hope we are on time. And please throw me a question, any of you have.
Yes, dear participant, if you have any questions, sir has covered very nicely for planning and placement in depth as an industrial aspect. What types of problems in a complex design, how to resolve using fundamentals. Any questions from participants? Sir, one appreciation, excellent presentation, sir, from the Mr. Ram Babu. Yes, it definitely is.
Thank you. Thanks for the appreciation.
Nice session, sir. Very informative session, sir. Yes.
So
Any
overall, I
questions?
think. So I'll just want to touch one more thing. So overall, if you see this thing, right? So this is the only place your floor planning and the kind of optimization. These are the only place where our core concepts of the semiconductors plays a very good role here, and the digital design plays a very good role here, right? So I think to reach here, and even if you can guide your students, so whoever wanted to pursue this career, right? So the basic fundamentals of your semiconductor, your CMOS, and the digital design plays a very good role here. And this is only the prime thing. Other than everything, you can build upon it. But these are the very much important things which we need to understand and gain.
Any questions, friends? So, let we end. Sir, you have spared the time for us, Mr. Vishal sir. And from your busy schedule, as we know, industry person, it's very difficult to spare the time as in such at a higher position, right? And also we know, okay, it's physical design. If any industry person, those who have worked really on it, and if they can take, then it is more justified. They can more justify because they have a real experience on it. How happening at a complex designing, uh, what are the issues and how to solve that issues. So thank you again, Mr. Vishal, behalf of Government Engineering College Rajkot, and myself, Koringa, coordinator of this event, and thank you behalf of me and all the participants.
Thank you very much. Thanks for listening.
Very nicely, sir. You have presented whatever the assigned you for planning and placement in all the details in the 2 hour duration. So exactly everything is very nicely happened. So thank you, sir.
Thank you.
Let me see if we have any. No, all. Yes, one questions. Sir, there is any opportunity for student as an intern at your organization interested in a semiconductor? So
Yeah, so I think you can ask your placement and departments to get in touch with our HR. Yeah.
And another one question is what 3 nanometer or 5 nanometer general talk about? So it is a technology. So, sir, you want to answer
Yeah.
what
So
is a 3
3
nanometer, 5?
nanometer and 5 nanometer, yeah, these are the probably a channel length what you have inside your gate, right? So this is what you have for each of the transistor. So with each shrinking technologies, right? So Foundry is also shrinking their best possible, and with 3 nanometers, so whatever you can achieve in 5 nanometer, that can scale down by huge numbers in the overall area. So if you shrink down the area, you'll save the lots of cost. So each foundry is always kind of trying to shrink as much as possible, and that will also overall kind of help you to shrink or last product. So any SoC you are building, if you can accommodate in a very less area, so that will overall help you to fit it in the lesser package or lesser board or lesser form factor, right? So that's what it is.
Okay, so if you do not have any questions, then we can end our session here. Again, thank you, Vishal,